So welcome everyone. Welcome to Birmingham. My name is Benjamin, and I have the pleasure to talk to you about high-speed processing and SQL. And when I got the name of this session, I thought that was really excellent because I love talking about SQL and I love talking really fast. So I've got an excuse for both. So what we're going to talk about are a number of advances in the Iris product over the past 2 years, a little bit since the previous time we had an in-person event. And to sort of tie it together, I thought of something that is typical UK and typical fast. Is there anyone who recognizes what this is? Yeah. Yes, so here's a little hint. This is Silverstone. This is your British Grand Prix Formula One roller coaster. Well, not really roller coaster. It's also Matt from the tech team told me that this is the new layout. Anyway, it's a very fast layout, and we'll use this to kind of tie a couple of subjects together and go through a couple of really fast pieces and a couple of very dangerous and tricky curves. So please carry with me. So the first thing we'll talk about is parallelization. So ABI is kind of the start of the sequence, at the start of the race. So this is where all of the race cars are still nicely aligned on the grid. They all have there's one in pole position and then one right next to it. So it's all nicely aligned. So what is parallelization? Parallelization is obviously the idea to accomplish a lot of work with more than one process. And the reason why that's interesting is very easy to visualize. If your work is to get 20 drivers across a finish line, it's faster to use multiple cars than to use a single car. So we'll talk about some of the parallelization things that we're doing within InterSystems Iris at the application level and at the kernel level. At the application level, we've got the automatic parallelization of SQL queries. So it's not always parallel because sometimes you need this low latency query that just does a single lookup to complete really, really quickly. And there's the setup cost of parallelization that you don't want to expense. So what we'll do is we'll identify from estimates of what we know that the data looks like, whether that's viable or not, and we'll automatically switch between a parallel and a non-parallel plan. For MDX, that's our BI query language, we'll always do that because we'll assume that an MDX query is always going to cover a lot of data. And that's also the nature of MDX, the way how the results are structured is also very, very well suited for parallel processing. Both of these engines and a couple of other parts of our platform make use of the same work queue manager. So that's our low-level, kernel-level infrastructure for queuing work and for having work processed by multiple workers. That API is available for your applications to use as well. So if you have an application that needs to accomplish a lot of work, take a look at a work queue manager. It's really easy to use. You just queue a bunch of work and you ask for it to tell you when it's ready. We've recently also extended that to cover workloads that need to span multiple machines. More about that in a little bit. Some of the things that are coming up soon are some tuning for that auto parallelization. So we first introduced the parallelization in 2016, and we've now realized that some of the constants and some of the trade-offs would benefit from a little bit of tuning. So we've done some proper benchmarking of that, and that's going to go into 22.3 release. And then also in 23.1 more likely, some automatic parallelization of when you're loading data. So we're still going to use only a single JDBC connection, but then both at the client and the server side, we're using multiple threads and a circular buffer to really speed up that querying. So this is a slightly more technical and quick introduction. We'll have a couple more meaty subjects later on. At the kernel level, so this is below the object script surface, there's a number of things that we've done. So we already were using multiple, or already offered you the ability to use multiple write daemons for writing to the actual database and to the which file, the write image journal that sits before changes to your iris.dat files. And we've now made sure that those write daemons can also help in writing to the which file, which we've seen has some really nice improvements in throughput, especially when combined, or at least it sort of depends on asynchronous I/O to be really effective, which is the default for Linux-based installations anyway. Another thing that's really, really fresh is multi-process dejournaling. So journaling is the first thing we do when you're trying to make a change to send to a global in your database. It's kind of a logical record that we write to a journal file. And if you have mirroring configured, at the far end of your mirror connection, we'll kind of replay that change before, even before it gets written to actual data blocks in the which file and then the iris.dat file. So now that far end of the mirroring connection can now also use parallelism to increase the throughput of your mirroring workload. Other things that are in this broader parallelization area are multi-process online backup. I don't know how many of you are using online backup or external backup. If you're not happy about the performance of online backup, this is going to help you. If you're not happy about the cost of external backup solutions that can meet your performance goal, this may also help you. So in both cases, please come talk to me because it would be very interesting for us to know if there's anything else we can do to make online backup really your preferred default going forward, because this is a big project that's coming up and that's going to be gradually rolled out in 2023, I guess. Okay, time for a next part of our track. So now we're kind of we've kind of gone through the loops. We've gone through left fields, which are two places where the cars kind of separate from one another. So now we're looking at not just spreading work across multiple processes that are still on the same node, but really talking about scaling it out across multiple nodes, across multiple machines, physical or virtual, however you want to deploy it. So we have two technologies in this area, one for scaling compute, which is called ECP, which has been around for a really long while, and one for scaling out across the data axis, and that's called sharding, and that is new in Iris, or well, compared to Cache, obviously, but it's been around since 2018. So first, the Enterprise Cache Protocol, ECP, is is actually a very unique protocol, a very nice low-level way how we've implemented a distributed coherent cache that allows you to deploy multiple compute nodes that sit in front of your data nodes and that can take in work, that can do work on behalf of your applications and that see the data as if it were local. And one of the great advantages of ECP as a protocol is that it's fully transparent. So whether your application is running on the data node in the most standard setup, if you're using the community edition and start writing some server-side code, it will run here. But that same application can run in the exact same way on the compute node. It wouldn't differ. It sees the same data. It has the same logical view of the data. It has the same transaction semantics. So that's really great for transparency for the applications. And also, if your application is running on a client, Java client, Python client, whatever you fancy, it also doesn't matter whether it's connecting to a compute node or a data node, or which of your, 100 compute nodes that you're running. So the transparency is a very important property of ECP. Another one is the elasticity. Spinning up an additional compute node is the time that it takes for the compute node to be part of this cluster is just the time it takes to spin up the infrastructure. The connection just takes a second or so, and then you can spread your workload across more machines. And spreading that workload means that you can also organize your workload. So our longtime partner Epic is making heavy use of ECP for their big deployments, and now increasingly they're deploying one set of compute nodes to support the user workload, and then a separate set of compute nodes for the utility that they deploy as utility servers. So that's for background processes, batch processes that were previously running on the data node, but running them on ECP nodes gives them better scalability. And by separating those from the user compute farm, if you will, ensures that they can use different subsets of the cache, and they're not kind of competing for the amount of memory that's available across. Some of the recent work we've done has also been with our primary, with our big partner in healthcare, Epic, to work on efficiency at the ultra-high scale. And I have a little more detail about that test that we did there. So the goal was to work with them very closely, deploy on the biggest cluster that we could put together. We had 100 compute nodes connected to a single really big database server, over 4,000 CPU cores in total. And the idea was to see if there were any bottlenecks at the application level, at the system level, at the hardware level that we could be working on in the foreseeable future. Because they have a horizon of at least 5 years, and they always want to make sure that they have a plan to cater to the capacity that they expect to need in 5 years. So at the start of the 2-week tests, we reached 350 million global references, but by the end, we had already found some low-hanging fruit, some contention on a very specific resource that was easy to address. And we have some ideas that we may be able to grow this to 1 billion global references a second. So now there's this kind of sporty challenge between the development group and the sales group to make sure that we meet 1 billion global references a second before we hit $1 billion in revenue. So on the data axis, so this was all scaling compute, scaling for actual work that needs to happen. If you have a lot of data and that data doesn't fit in the database server that you would allocate in a classic ECP-only scenario, you can also spread it across multiple data nodes and link them together. So this is what we use in SQL and objects to distribute work. And the two main properties of sharding is that it is transparent in how it manages your data. So if you connect to a single node and you start inserting data, it will transparently be distributed evenly across all of your data nodes. So you don't have to worry about it. It opaquely distributes the data across those nodes. And the reason why it opaquely aims for an even distribution is to make sure that the actual work, when a query comes in, can also be distributed. And that any work that is tied to the amount of data that needs to be handled gets, that every node has kind of the same amount of work that it needs to do. So this has worked really well. And some of the recent work that we've done in this area has focused on elasticity. So making sure that it can also dynamically add and remove data nodes, and that we can rebalance the data to, again, aim for that uniform distribution without interrupting your queries, without interrupting your workload. And we've removed a couple of older limitations on what you can do on the schema design side. Okay, time to get into a trickier part of our platform. So maggots and the Beckett's curves. On websites I consulted, because I'm not a huge specialist in the Silverstone circuit, or any circuit for that matter. These are the most beautiful turns in the most beautiful curves in the whole of Formula One. So this was a British website that I visited. I have no reason to believe otherwise. But anyway, so these curves are very complicated to navigate. This is probably one of the slowest parts of the whole track. So it's important that you have a good plan when you go into those tracks. And this is a website. Also, it wasn't the website that I was frequently visiting before, but it's raceoptimal.com. And it has these nice, it's probably hard to see in the back, but these curve lines that you have to follow that are the ideal ways to progress through your track. So this is based on profound analysis that takes into account the properties of your car, because you can select different curves for different cars, standard road conditions, standard weather conditions. So that's the default plan. So this is to have your best ever race. So this is because the Silverstone GP is 52 tracks. You don't want to have to figure out each time you pass for those 52 times how exactly you need to drive. So you want to start with a good plan. But then in reality, this happens. There's Extinction Rebellion that has a picnic right where your line is. So you need to adapt your plan. You need to figure out a plan that takes into account the runtime context. And that's what we also do in InterSystems these days. So this is, if you're interested, I have a much broader session about this from Global Summit that you can consult at learning.intersystems.com. But this is in a nutshell how InterSystems processing works. First, we'll look at your query and we'll parse it. We'll check if it's valid and if the tables exist and whatnot. Then we'll figure out a plan. We'll do what the guy from raceoptimal.com did for the racetrack. We'll figure out possible ways to navigate through the tables and find out, should I use this index or that index, or can I combine them? What is the most appropriate join order? And then very closely related with that, we'll try to estimate a cost, an execution cost, for each of the viable plans. And then for the one with the lowest cost, that is presumably the most efficient one, we'll generate the code, the object script code, to actually execute the query, and we'll run it. So that's the default plan. And what we're doing to make this reusable, because this is complicated, especially the planning and costing stages are very computationally costly, is that in the parse step, we'll take all of the runtime things out of the statement. So if you're doing a select star from transactions where ID equals 123, that 123 isn't going to make a difference for the plan. You're just making that a parameter, and you parameterize your plan so that you can reuse it with, if you need to check not record with ID 123, but with 124, because the plan is probably going to be the same. So we reuse the generic plan, we cache it, we cache the code, we cache the plan. Very efficient. This is served really well for the majority, for all of our customers. But then there's the picnic moment. Then there's a picnic that turns out. So what we've done now with runtime plan choice is at runtime, at the very start of our generated code, we do a really quick check. Is there a picnic? Is there something in my runtime parameters that would recommend me taking a different approach, taking a different plan? And if that is the case, I go back to the planning stage. I take into account the outlier. I take into account the picnic, and I cost code and then run that plan. But that plan obviously now also goes into the cache with appropriate metadata about the specific conditions, so that next time I pass by the picnic spot, I can just pick up that plan and proceed in the same super efficient way as under default conditions. So it took us a long while to make sure that we have that runtime check really, really fast, because you don't want to slow down the simplest of lookup queries. But now it's part of the Iris SQL stack. When will we perform runtime plan choice? We'll do it in the case of outlier values. So imagining a log table. I wish for all of you that the vast majority of your log table is full of info records and not errors. So if you are selecting all of the info records, then going through the level index is probably not so helpful, because you'll be going through the majority of your data. So that's an outlier. There's a particular value covering a disproportionate amount of your actual rows. Another interesting case that we're implementing runtime plan choice for is range selectivity. So in this case, if I'm checking for all of the records from the last minute, or if I'm checking for all of the records from the last year, that's also going to make a difference of whether it's suitable to use an index on that date field or not. And then finally, truth conditions. This looks like quite ridiculous, but you would be surprised how many tool-generated queries or application code contains this kind of queries where at runtime they can just feed in a different parameter and knock out a whole part of your where clause, or knock out a whole part of your query plan. Obviously, these are cases where your query plan may change drastically based on those runtime values. So that's another case where we do runtime planning. So this is kind of a zoomed in part of the chart that Jeff showed you yesterday. We started 2020.1, which was already a lot faster than Iris 2018.1, which is already faster than Cache 2018. And then in 21.1, we had some small improvements in code generation, etc., and also at the lower object script runtime level. But we were really kind of saving our thunder for runtime plan choice, because boom, we kind of cut the time it takes to run this benchmark in half by using this smart runtime plan choice check, and we were able to limit the I/O to 75% of what it was before, giving you exactly the same results, but just faster. So that's what adaptive SQL means for Iris. The next subject I wanted to talk about is columnar storage. So I've tied columnar storage to the hanger straight. This is where you get top speed on on the where you get top speed on the Silverstone track. By the way, you probably figured out after watching Carmen's session and now my session that it's in our annual appraisal that we have to take Jeff's analogies. So what is columnar storage? In order to explain columnar storage, I first have to briefly sketch the difference between applications and analytics. So this is a typical query for an application. So for a particular customer, fetch the 10 most recent transactions so that you can show them in the banking app. And this would be how that data comes about. You're entering a transaction. It's a little dense, sorry about that. But anyway, you're inserting individual records, you're updating individual records, and you want it to be done really, really quickly because you want to make sure that if you're trying to make a purchase, that you don't have to wait half a day before the system confirms that, yes, there's enough money on your balance. So low latency, very small row-oriented work. So fast inserts of individual rows. You're interested in the whole row because you need to show it in the app. And the focus is on latency. And you're going to store the data, how it's used, row by row. Now, this is another query that could be looking at the same schema. So now I'm not looking at my banking app where I want to see the most recent transactions, but now I want to analyze the transactions for a whole year. So for the past year, still for one particular account, but now I want to not give me all 200,000 transactions. Sorry, I pay a lot. But you want to group, you want to aggregate, you want to have the average and the maximum amount grouped by type and by month. So that's a wholly different type of query. You're going to be looking not at 10 records, but you're going to be looking at potentially hundreds of thousands of records. Also, the way how this data comes about is by loading the data in bulk, often from a file or from some other sources. So that's very different from the model that we saw in the application case. So complicated queries on large amounts of data that return aggregates and not full rows. And the focus really is on throughput. You know that there's a lot of work that needs to be done. So you want that work to be done as efficiently as it possibly could. The time it takes to give you the first row is not as important as the time it takes to get the last row, because you really want that last row here too. So that's storing the, so here the guidance would be to store the data how it's used, column by column. So that's what we do in columnar storage. Columnar storage is a new feature in InterSystems Iris. We're going to release it as an experimental capability with 22.2 later this month. And it really gives you the option to store your data in row storage, like the classic way how we're doing it now. So your logical table gets stored with in a horizontal way, so one I/O for one row. And we're going to add a new option there that is columnar storage. So we're going to store the data column by column in chunks of 64,000 values so that it aligns nicely with our bitmap indices for that analytical use case that I just talked about. So just a little more about how we optimize that storage. So for row storage, we've always been using our $list data type, which allows you to encode multiple values in a very flexible way. The key word about $list is that it is flexible. You can add different data types, you can chain them together and just put all of the data in your for one row in one global node. Obviously, in your table, you want to have the flexibility of having multiple different column types. So that's what $list gives you. And the latency is achieved by storing one such $list per global. So you get the whole row's data with one I/O. In the columnar world, we're introducing something new called $vector, which is optimized for something else. It's not aiming at flexibility, it's aiming at high performance operations, and also high performance storage by encoding 64,000 values of the same data type, because we're talking about one column, into a compact representation. So we're exploiting some of the peculiarities of the data types. We're exploiting sparsity when we can, all dynamically so that you don't have to worry about it in that new data type. And there the focus is really on throughput. So that was the storage side. Now a little more on the processing side. So with $vector, we're introducing a bunch of $vector operations that look at that chunk of 64,000 values of the same data type, and we handle them all at the same time. So that allows us to exploit some of the strengths of modern CPUs, including those SIMD instructions, single instruction, multiple data, so that you can have super efficient summations and other aggregate operations. It exploits some of the lower level things like how modern compilers can automatically vectorize work that gets done in tight loops. So a lot of that is all encoded inside $vector, which is an internal data type that we've built for columnar storage. So we're taking advantage of that in our SQL processing by really taking those $vector pieces and pushing them throughout our query execution plans. So rather than first storing it by column and then iterating through all the values, we're going to really try to push the entire 64K chunks of values throughout our query plan, and only at the very last moment, only if a user really asks for a row, we'll materialize it. But we assume that in the majority of cases, they'll be looking at an aggregate, and that's where these $vector operations can offer really fast performance. That whole layout also gave us an opportunity to implement a new parallel query execution strategy that kind of encodes everything in the same cached query rather than regenerate subqueries, which was our classic approach. And we're going to be rolling this out to other non-columnar SQL as well. So that's also something really exciting because it will allow us to more dynamically change the degree of parallelism based on the current workload. So very promising evolutions there too. And the net goal of this whole project is to make analytical queries 10 times faster. And based on the proof of concepts or the early access program work that we've done with customers, we're really meeting that goal. So it's very exciting. If you're interested, if you have an analytics use case and you're interested in giving this a try, you can use the developer preview or very soon the GA release of 22.2. And if you want some help, if you have some feedback, please get in touch. We'd be thrilled to work with you and see what it means for your business, whether it's 10x or 100x. It really depends on the query. Some queries we had one that was 6,000 times faster. And then others that were 7, I'll be honest. Okay, the last part of the track I wanted to talk about, very hard to escape, you wouldn't be able to do a race without passing through it, is the pit lane. So in the pit lane, it's all about smarter operations. It's all about having a crew that helps you keep your race car in top condition and making sure that you can keep driving your race. So just a few words on what we can do there is we can do this for you. So I've been talking about 4 different subjects of pure performance that sits in the platform that you can take advantage of by just upgrading. But why would you do the upgrade? Why would you not leave it to us to do the upgrade and manage your systems? So by deploying to our managed services or our SaaS offerings, you immediately take advantage of our best practices that Jeff was explaining in the previous session right before the break. So agile deployment using our cloud core architecture, implementing best practices around observability and monitoring, security, upgrades, all taken care of for you. So as I mentioned, we have a number of managed service offerings, and then also the full software as a service cases where you really don't need to worry about anything called an instance at all. So that's it for my talk. I hope we have a little bit of time for questions, but I wanted to just wrap up by saying that our goal is to keep moving the needle. We're never finished. As you saw in the slide about the lab tests that we're doing around a 100-node cluster, ECP cluster, we try to keep pushing the limits. 600 million global references a second is not enough, even though it's almost 10 times what their biggest deployment does today, biggest real-world deployment does today. We want to make sure that everything we do is transparent to your application so that you don't have to worry about anything other than the functionality of your application, and that will transparently make it faster release after release. And finally, if you really want to focus squarely on your functionality, let us be your pit crew. Let us do the heavy lifting of well, not so heavy, the managing, monitoring, and maintaining your systems. With that, I think we have 10 seconds for questions.